is a new video under the analysis of statically indeterminate structures, and I'm going to talk today about the slope deflection method, and I'm going to talk about an introduction for it. Okay. Now let's talk about the introduction. Actually, there is something that needs to be recalled first before going into the slope deflection method. Already I have touched upon this point before, but it's better to recall it again and revisit this point again, which is the flexibility versus stiffness method. Okay, so we are, before in the previous lectures actually, we considered the force, which is, we call it the flexibility method. So we were considering force as our main unknown, and we are working upon this. So our main unknown is the force. So recall that in the force method, the unknown redundant were forces. Okay, the forces are determined from the compatibility equations. Then the other response characteristics of the structure are evaluated by equilibrium equations or superposition. So we start like this, that we go with compatibility equations, and after that we end with equilibrium equations, right? This is the flow where that we were what we were doing in the flexibility method. And remember that the unknown redundant were the forces. Forces were our main redundants. Okay, so now we are going to talk about the slope deflection method, and it is considered to be from the stiffness methods, or considered to be among the stiffness methods that is available for us. So an alternative approach that can be used for analyzing indeterminate structure is termed the displacement, or we call it stiffness method. Okay, so in comparison with the flexibility, it was here force or flexibility, here displacement or stiffness method. Unlike the force method, in the displacement method, the unknown or displacements are determined first by solving the structure's equilibrium equation. Now we start with equilibrium equations. Then the other response characteristics are evaluated through compatibility considerations and member force deformation relationships. So this is an important issue that I want you to remember. Here we're starting from compatibility to equilibrium in the flexibility method. In the stiffness method, we start from equilibrium and go to compatibility. Here the unknowns are forces. Here the unknown are displacements. Okay, so this is an important issue to keep in your mind whenever that we are thinking about the stiffness or slope deflection method. So now let's talk about the main concept of the slope deflection method. When a continuous beam or a frame is subjected to external loads, internal moments generally develop at the ends of its individual members. That's very true. Whenever that we have any member and we have any distributed load with any kind, whether it is distributed load or concentrated load, due to these concentrated or this external load or these external loads, there is what we call it internal, or there are internal moments are going to be developed. There are something would be developed here, like fixed end moments, and there are some end moments are going to be developed at the ends, and also shears and so on. So due to the external loads, there are straining actions will take place in the beam, and then end moments will develop at the ends of this beam. So internal moments generally develop at the ends of its individual members. Okay, that's known and we understand it. The slope deflection equations relate the moments at the ends. Now the role of slope deflection equations, to understand it, it is going to make a relation between these moments that is going to be developed at the ends of the beam and it is going to relate it with rotations and displacements of its ends and the external loads. So as if that the slope deflection method is going to relate first moments at the ends with two things, with rotations, okay, rotations or displacement and displacement, okay, they are in the same category, with external load, external loading. So now we can understand that the moments that is going to be developed at the ends of the beam is going to be related to the rotations, because whenever there is moment that is going to be developed here, if we have this end, sure that there is some rotation, there are some, here it is fixed, so there is like the rotation here is going to be 0. But if we are having a continuous beam, something like this, there is some rotation going to take place, okay, and there is a slope for the elastic line before and after our support. So the slope deflection method is going to relate between the moment and the rotation and displacement from one side and the external loading from the other side, these loadings that is being applied, okay. So that's the main idea. The slope deflection equations relate the moments at the ends of a member to the rotations and displacement of its ends and the external loads applied to the member. We're going to see this and understand it clearly during our explanation and the examples. Okay, now let's understand the main concept. Let's assume that we have this beam. As you can see here, it is this beam. It is loaded with external loads, B, and distributed loads here. This is the undeformed position, and this one is the deformed position, which is, we call it commonly, the elastic curve. After the settlement of the supports and the deformation of the beam main cross-section. Let's go and study this section of the beam between A and B, which is having a length of L, and we are going to magnify it a little bit here so that we can understand. Still we have the distributed load and the concentrated load. All the external loads are going to be there, our L here, and what will happen for this section is going to be the derivation for whatever that equation that we are going to have here. It is going to be found in detail in the textbook, but I do not want you to go into the details of it. Just you can read it once and understand it, and then what I want you to know is the main idea. Whenever that this beam is going to deform under the external load, so let's assume that this is its undeformed position, which is, we call it undeformed position with the dotted line here. After applying the loads, it is going to deform in this way. A would be A prime, and B is going to be displaced till it reaches this point, which is B prime. Okay, and then the shape itself of the elastic line of the beam between A and B is going to take this shape. As you can see, we call this, as we said, the elastic curve. The elastic curve. There is a dotted line that connects between the end, the first end, which is end A prime of the deformed shape, and the other end of the beam. We call this dashed line as the chord. Okay. The angle between the dashed line or the chord and the horizontal, we call it psi, and it is going to be the same at both ends. For the rotation angle that is going to take place at end A, it is going to be between the horizontal and a tangent at the point A of the elastic line. We call it theta A. In a similar fashion, we can assume that the angle between the horizontal and the tangent of the elastic line at point B is going to be theta B. So these are the annotations, important annotations for us. What I want you to understand that in the slope deflection method, there are a great deal, you can find the derivation as I said in the textbook, but I want you to understand this equation, which is the final step of the derivation. We're going to say that the moment at end A toward B, which is we call moment AB, means that at point A, okay, as if that we are having, this is like M moment AB, however here this is moment B toward A, okay, so we can call them like this. So MAB, which is M at the, if we are talking about the moment at point A, so this is the near moment at point A. So we say that the moment that is near to A and far from B. This is the meaning of MAB. Similarly here, whenever we say that it is MBA, it means that the moment that is near to B and far from A. Okay, that's the meaning of the annotation. So whenever we say MAB, it means this moment at point A. It equals to, there is a contribution of the stiffness and the length of the member itself. And this contribution is going to be through the inertia, which is EI. This is Young's modulus. This is the inertia of the cross-section, and this is the length. So this is the first contribution, the member properties, times some angles here. These angles are theta A and theta B, and we know well what is theta A and what is theta B, and 3 psi minus 3 psi, which is the chord. So this is the contribution of the deformation of the elastic line of the beam itself, plus the contribution of what? Of the external loads. The contribution of the external loads is going to be indicated through the fixed end moment. I'm going to talk about it in detail, but the fixed end moments is whenever that we have any beam, we are going to consider that the both ends are going to be fixed, and if there is a distributed load, there is some end moments are going to be developed. These moments are due to the external loading. So this is the contribution of external loading. We call it fixed end moments. So we have like 3 different contributions. One part related to the properties of the beam. Another part is related to the elastic line deformation of the beam. And the third part is related to the external loading that is applied. Similarly, we can apply the slope deflection equation at point B. As you can see here, we can say that MBA, which at this moment is going to equal the same 2EI over L. And here the same as here, but take care that A here, it is multiplied theta A, it's multiplied here by 2 whenever that we are talking about AB. But whenever we are talking about BA, it is A, only theta A, and 2 times theta B, which is 2 times the far, 2 times theta B, which is the theta B, is going to be developed here, minus 3 psi, the same, plus FEM, the fixed end moments BA. So what is the meaning of fixed end moments BA? It is, as I said here, this is fixed end moment that is going to be from A to B. However, this is going to be fixed end moment from B to A. Okay, this is the difference between them. Actually, they are like 2 equations, but if you look deeper, you're going to find they are 1 equation. We need to think about the word near and far, right? I was talking about near and far. So here we can say And instead of saying that MAB and MBA, we are going to say that the moment which is near to the point that I am going to talk about, and this is why the subscript here N, and it is far from the other end, which is, for example, if we're talking about MAB, so here N is going to be A, F is going to be B, and then 2EI, 2 theta N, like 2 theta A, plus theta F, which is B, theta B, minus 3 psi, the same, plus FEM, NF, AB, right? If you are going to apply it to the other way around, which is MBA, you are going to find that B, it is the near, A is the far. Also, it is the same, it is right. So if we're going to say that here, we apply this, the second equation here, to this general equation, it is the same. M, B, A, because B is going to be the near. So N stands for near support. And F stands for far support. So here we have near, it is B, because we are talking about the moment here. And the far is going to be the point A. So it is going to be MNF or MBA. And you are going to apply N and F. It is B and A. So it is B here. It is going to be B here, which is multiplied by 2, and this is right, which is the near, and A, which is the far one, which is 1, and minus 3 psi, and the fixed end moments is going to be NF, which is BA, right? So this equation is very important, which is equation 16.9 in the textbook, and we call this is the slope deflection equation, general equation, the slope deflection general equation, okay? I hope that you understand this very well and take care of this equation because it is really important. Okay, now let's go to the, this is actually the explanation of what I was saying. So this is the equation, the general form. This is the what I have explained in the previous slide. So actually M and F, N here refers to what? Near end. And near end where that the moment that I'm studying, okay, yes, and F indicates or identifies the far end, okay, so F identifies the far end. So this one is applicable to any equation, okay, so it is applicable to any equation. If I'm talking about this moment, so we are talking about near, which is A, far is B. If I'm talking about this point, then B is near, A is far. Okay, and then you can apply this equation directly. Okay, remember well, this equation is very important. Okay. The fixed end moment expression. Let's talk about the fixed end moment expressions. The fixed end moments expressions for some common types of floating conditions are given inside the back cover of the textbook for convenient reference. Actually, I have only I want to highlight that in this equation we put fixed end moments. So from where we can get this fixed end moments? There is some equations, you can find it in the textbook, but I prefer to use the reference in the back cover as we said in the textbook. We're going to find it in the back cover, you're going to find these references. So what is the meaning of fixed end moments? Fixed end moments is whenever that we have a beam, continuous beams, for example, okay, whenever that we study one section, if we say this is A and this is B, a section of the beam, then we are going to assume it to be fixed from both ends as long as this is continuous above the support, there is no link or there is no intermediate hinge, then this end is going to be fixed and this end is going to be fixed. From here it comes the word fixed. Fixed end moments means that there is continuity here, so there is moment is going to be developed above the support and we are going to deal with this section as if it is fixed. Then we have said or we found that we can put a different shapes of the beam with different loading conditions, and we can get the fixed end moments at the two ends of the beam. So we're going to find, for example, the distributed load, the fixed end moments. The famous one is WL squared over 12, WL squared over 12 from the both sides. If you have one concentrated load, it is going to be PL over 8, PL over 8 from both sides. Commonly, you are going to use them because whenever that you are going to apply the slope deflection method, you are going to revisit this reference many times. I put all the reference here in these slides so you can check them conveniently for different loading and different types of loading, including some settlement of the support. So if we have a unit settlement delta at one end, so what is the moment that is going to be developed? It is here 6 EI delta over L squared, and here the same also. If there is a rotation moment, which is unit radiant, for example, so the moment is going to be 4 EI theta over L, and here is going to be 2 EI theta over L. Okay, so this is the fixed end moments for all the conditions that you might face whenever that you solve such kind of slope deflection methods or problems. Okay. Now let's go to the members with one end hinged. Sometimes whenever that we are, or sometimes we encounter a beam that is at the end there is like hinge. We have here, something like this, for example. So whenever we study, they are like rollers. Okay, and even this is roller or hinge, but anyway, when we are studying about this section, this part, this length, this is fixed because there is continuity over the support. Here between this section or between this point and this point, they are also fixed. But at the end here, we're going to find that this one is fixed, so it is fixed here, but here it is not fixed. It is what? Yes, it is hinged. So how we can apply the slope deflection method? For this case, we put it as a special case, members with one end hinged. In this case, the slope deflection method is going to be designated with R and H. So R refers to rigidly connected end, which is this end. This is the rigidly connected end. We call it R. And the far end is going to be H, which is hinged of the member, where that the moment MRH acts. Actually here at this fixed end, it is here the moment is going to be MR because this is the near end, H, which is the far end. Okay, so the moment that is going to be developed here called MRH acts, and the subscript H identifies the hinged end of the member. This is the hinged end of the member. The rotation, so how we can say that is MRH, so the moment that is going to be developed here, remember that there is no moment will be developed at the hinged end because it is hinged, no moment. So MRH is going to equal 3EI theta R minus psi plus fixed end moments RH. There is fixed end moments can be developed here. Okay. Minus fixed end moments HR over 2, which is the moment that is going to be the fixed end moment that is going to be developed at the far end here. Okay. We're going to see these are some cases where that we want to apply this equation. Okay, and remember that MHR in our case it is going to be 0 because we have a kind of a hinge here, so there is no moment here, right? So this is going to be 0. So MHR is going to be 0. Okay, based on this, theta h, it is the, if we have the moment here, the elastic line that is going to take place here. So this is theta h, okay? So it is going to equal theta r, which is the rigid theta, okay, over 2 plus 3 over 2 psi minus L over 4 EI times the fixed end moments HR, okay, HR, fixed end moments, that is going to be developed HR at the hinged end, okay? Okay, so take care that this is MHR and this is fixed end moment HR. They are different. The moment that is going to be developed at the end is going to be 0, but the fixed end moments that is going to be developed, that we are going to use here, it is going to be divided by 2. Okay. Now let's go to another part, which is basic concept of the slope deflection method. Okay. I'm sorry, I think that there's some problem here. This is not related to the least work at all, so forget about it. Okay. So let's talk about the degrees of freedom. We're going to talk about an example, and this example going to give us or help us in understanding the whole equations and the whole process. If we have a beam, as you can see here, which is having a fixed support at A and roller support at B and C and fixed support at D. First of all, whenever we look to this beam, we are going to say that first question that we should ask is, what is the degrees of freedom of this beam? The degrees of freedom commonly is going to be the points where that rotation or displacements are available or they can occur. So let's check here our beam. We have A and we have D. They are fixed support, right? And commonly whenever we have a fixed support, so the rotation here and here is going to be 0, right? So there is no degree of freedom here and here. But look to the point B and point C. The elastic line at these points, at the supports, can deform in the way that you can see here, right? We're going to have theta B before and after the point support B, and we are going to have theta C, which is the rotation of the deformed shape at point C before and after, right? So we can say that these unknown joint displacement are referred to as the degree of freedom of the structure. So we do not know what is the theta B, how much rotation is going to take place here, and how much rotation is going to take place at point C, which is theta C. So we have theta B and theta C. So it is, this structure is twice, is having 2 degrees of freedom, 2 degrees of freedom. The continuous beam has 2 degrees of freedom, theta B and theta C, which represent the unknown rotations. These are the unknown rotations of joints B and C. Remember that we are talking, as we said in the first slide, we're talking about the slope deflection method. Our displacement or rotations are going to be our main redundant or our main unknowns. So we are talking about this right now. Okay, so now from this example, we are having all the information. We have distributed load in the first span. We have a concentrated load in the second span, and there is no loading at the end span. We know all the length, and we have all the information available for us. So we now have all the input data for applying our slope deflection method or equation that we have explained in the previous slides. Okay, let's go. Now let's go with the slope deflection equation. We want to apply them. Okay. First of all, before going and writing the slope deflection, we want to look to the whole beam as separate beams. So we're going to say that we have AB, which is the first span, and then we have joint P alone, and then BC, which is the second span, and then point C alone, and then the third span, which is CD. This is what we call it the free body diagram for all the components of the beam, right? So for the first span, we're going to deal with an external load as distributed load only. In the second, we are going to deal with concentrated load. And in the third, there is no loading at all. Okay? So this is something that we want to understand. Okay, before going into the slope deflection method, we need to make very important thing, which is equilibrium equation establishment. Do you remember when we were talking about, let's go to the first slide, or maybe the second one, that I said that the main concept. Yes, here the main concept, we said that we are, I think in the previous one, yes, here. So the displacement, unknown displacement, are determined first by solving what? Structure equilibrium equation. So we start with equilibrium equation. Then the other responses characteristics evaluated through compatibility, right? So we start from equilibrium, go to the compatibility. Now let's go here to our case. Yes, here we are. Yes, so we need to start with what? Equilibrium equations. So where the equilibrium here? Where we can start the equilibrium? Because the entire structure is in equilibrium, each of its members and joints must also be in equilibrium. That's very true. By applying the moment equilibrium equations, summation of m at point B equal to 0 and summation of the moment at point C equal to 0, respectively, to the free bodies of joints B and C. So we are going to look to this free body diagram of point B and the free body diagram of point C. This is point B and point C. We are going to apply summation of moment at B equal to 0. This joint must be in equilibrium. Same for this moment. For this point, the summation of moment at point C must be in equilibrium, should equal to 0, right? From here we can look. Look to the first span. We know that there are some moments here would be developed, which is MAB, and in the far end there is MBA, right? And for this span, the moment that is going to be developed here, MBC, and the moment here is going to be MCB. Similarly here, MCD, and here MDC. We are sure that these moments are going to be developed, but we do not know them. We do not know what is the value, what is the magnitude of each of them. But we are going to apply the equilibrium equation at point G, at every point which is at the points of the support. If we take the free body diagram of the support at point B, we will have that this MBA with this sense is going to be reflected in an opposite sense here, which is going to be also MBA in magnitude, but the sense is going to be different here, okay? Because it should be always the different in order to maintain equilibrium. You're going to ask me from where we got this sense, which is the direction that is counterclockwise of MBA. Actually, we didn't get it from anywhere. We assume it. So it is not, maybe it's not right. Just we assume anything now. And we are going to find whether our assumption was right or wrong. Okay, so now let's go back to the equilibrium equation for point B and point C. Equilibrium equation at point B would give us this simple equation. That is MBA coming from this span plus MBC, which is coming from this span, should equal to 0, right? This is very true. Similarly, we are going to apply the equilibrium equation at point C. at this point, you're going to find two different moments, MCB and MCD. Their summation should be equal to 0. MCB and MCD, and they should equal to 0. Okay, so this is the first thing that we should be sure of, which is the equilibrium equations. Okay, let's go to the next part, which is related to something important before indulging into the slope deflection equations, which is the sign convention. I put it in a very bold and very big because many of you are forgetting it. Okay, remember that it is very important. The slope deflection sign convention is counterclockwise fixed end moments are considered positive. So remember that very well. Counterclockwise, if there is something counterclockwise, it is positive. Anything clockwise, it is negative, especially whenever that we're talking about fixed end moments. Okay, remember this slide very well. Okay, now let's go to the next. Let's go to the fixed end moments first, and then we're going to apply our slope deflection method or equations. Let's now start with the member AB. This is member AB, right? So for member AB, we're going to say that there is external loading, which is distributed loading, right? And we have fixed ends at the both ends. We have fixation here, and here there is a roller, but it is continuous. So there is moment will be developed here. So it is considered as if it is fixed. There is moment would be developed. So we are going to put the analogy as this is point A, this is point B. You can find this in the references of in the back cover of the textbook. You will find that distributed load with fixed end moments for this case, which is spanning L and W distributed load, which is the first case as I mentioned before. Then here, the moment here, or the moment that is going to be developed here, it is going to be what? M. The near end is A, the far end is B, right? And here, from within this member or span AB, the moment that is going to be developed is M, the near end is B, the far end is A. Okay? So, this moment is going to be MAB, fixed, I'm sorry, not MAB, it is fixed end moments at AB, so we're going to have fixed end moments at AB. It's going to be WL squared over 12, which equals to 1.5 times 20 squared over 12, because we have 1.5 distributed load. It gives us positive value, right? It is positive here. Positive means what? Yes, exactly, counterclockwise. This is counterclockwise. Fixed on moments at AB, it is counterclockwise, which I applied here, as you can see, counterclockwise. And for fixed end moments BA, which is this one, this is the fixed end moments, WL squared over 12, it is going to be the same and positive as well. And, fixed end moments is going to be, remember, that we are talking about, it is clockwise here. So it is going to be negative. It is going to be negative. And this sense, which is clockwise, it is going to be applied here the same. It is clockwise, value 50. Okay, now this is for member BC, AB. Now let's go to member BC. We're going to find that we have two fixed end moments. Fixed end moments at B, which is FEM BC, and here it is going to be FEM CB, right? The first one, it is from the reference back cover, PL over 8. So this is what? Exactly, it is counterclockwise, so it is positive. And here it is the same magnitude but different sign, it is clockwise, so it is negative, right? So FEM BC, it must be positive. However, FEM CB, it must be negative, as you can see here. Then we're going to apply them as they are on our beam. which is 75. We found that they are going to be the same, 75 and 75. So here 75 and here to 75. Counterclockwise, clockwise. Okay, what about this? The last span, CD, if their fixed end moments will be developed, the answer is no. Why? Because there is no external loading. So this is what I put it here, that FEMCD equal to FEMDC equal to 0. There is no fixed end moments will be developed here because there is no external loading. We said before that fixed end moments are considered to be the reflection of the external load applied on the system. Okay, now we know the fixed end moments, right? And we have the equilibrium equations from the previous. Now we have the equilibrium equations and we have the fixed end moments. Now let's go to exactly the slope deflection equations. Let's go to the slope deflection equations directly. This is our main equation that I said to you that you need to memorize. MNF 2EI over L 2 theta near plus theta far minus 3 psi plus FEM and F. So now let's apply our equation, slope deflection equation. We are going to apply it at every point available for us. We're going to apply it at point A. So we want to get the moment, which is MAB, right? The first moment MAB. This moment is going to be 2EI over L, 2EI over 20 times 2 theta n. 2 theta n. What is theta n here? It is the rotation at point A. It is fixed, so the rotation is going to be what? 0. So this is why it is 0 here. Plus theta b, which is the theta at the far end. It is here, theta b, right? So it is a value that we do not know it. It's theta b. Minus 3 psi. What is psi? It is the chord rotation angle or the chord angle with the horizontal. Actually, as you can see, point A and point B, they are on the same line. Even that we have some elastic line here, but they are on the same line. This means that the chord angle with the horizontal is 0. So we have this to be 0. So this is going to be cancelled because we have this to be 0. Plus fixed end moments NF, which is fixed end moments AB. We already obtained it from the previous slide, which is 50. Apply this and you are going to find that there is one unknown in this beautiful equation, which is theta b, right? Okay, now apply the same slope deflection method but at point B in the span AB. So we're talking about this point. 2EI over 20, 2 theta b, take care, 2 theta near, theta b, plus theta far. What is theta far here? It is theta at A, which is 0. That's right. Minus 3 psi, which is 0. Then this is the fixed end moments at MBA. Take care of the sign. It is minus. From previous, it is minus, right? Okay. So we can obtain this equation. So we have equations now, 2 equations. When we apply slope deflection method at point A and then at point B, and all of them they are in terms of theta b, which we do not know it. Then similarly we are going to apply the same equation for member BC. Okay, we are going to apply it for member BC. So the slope deflection method is being applied on each member. So this is member AB, this is member BC, and then member CD. Okay, for both sides. So for member BC, in a similar fashion, we need to get 2EI over 20, 2 theta b plus theta c, because we have the psi to be 0. Here you are going to find theta b and theta c because we are in the middle, right? So here the far end is theta c and the near end is going to have theta b. So we have theta b and theta c. There is no psi because psi is 0. Psi is 0 in everywhere because we do not have any settlement support, so psi is going to be 0. Plus the fixed end moments, right? Fixed end moments NF, near to far. Here We already obtained it before. It is 75. Here, the fixed end moment at C is going to be exactly negative. Take care of the sign. Here is positive, here it is negative. Okay, so we found that our equation is not only in theta B, but it's in theta B and theta C. Similarly, for this moment, it's going to be in theta C and theta B. Okay, so we are going to find that theta B and theta C are the main unknowns for us, right? As we said before, they are the rotations. Let's assume, or let's apply our slope deflection method at the lost span CD. So MCD, we have 2EI over 15, its length, 2 theta C. Why 2 theta C? Because the other two, theta 4, which is the fixation at D, it is 0, and 3 psi, it is 0. So we have 2 theta C only. This would give us this amount in terms of theta C. Similarly, in the moment at DC, it is going to give us this amount for theta C. So if you look here, all the moments are function of what? Theta B, theta B. Here it is theta B and theta C. Similar here. Here it is theta C. Right? We have all of the moments at all of the points. They are function of the rotation. This means that if we could find the rotation, we are going to obtain the moments easily. So how we are going to find these rotations? Yes, exactly, from the equilibrium equation. Right? From the equilibrium equation, yes. Then look to the joint rotation and our equilibrium equation. In the beginning, we said that MBA plus MBC should equal to 0. This is from the equilibrium of the free body diagram of joint P. And this equation from the equilibrium of the free body diagram of point C. So, MBA, we know MBA. From here, it equals to MBA, right? Because remember that we are talking about the point C, point B, sorry. So we are having, I want to show you this equation. So at point B, okay, I want to show you the other one. Yes, here. So this is our free body diagram of the joint. So we have MBA and MBC. They should be, the summation should be 0. Right? Okay. So now we have MBA. We obtained it from here. This is MBA equals to this amount with theta B. And we have MBC, which is going to be MBC, which is 0.2 EI theta B, blah, blah, blah. This one. So here we put it like this. This is going to be MBA, and this, the second and the third and the fourth term, they are going to be MBC. Now look to this equation. If you are going to rearrange it, is going to boil down to what? Yes, something times theta B plus something times theta C. And we are going to say this is equation number 1. In a similar fashion, we are going to substitute with MCB, which is, we already calculated before, as theta C and theta B, function of theta C and theta B. And we have MCD, which is 0.267 EI theta C. Rearrange it, you're going to find that it is function of theta B, theta C, and equal to something. So this is equation 1, theta B and theta C equal to the right hand side, two equations in two unknowns, theta B and theta C. You can solve it by your calculator very easily. Then you can obtain from these two equations, you can obtain theta B and theta C very easily. Take care of the sign convention. Theta B, when we calculate, we found it minus 0.001 rad. This means that it is 0.0011 rad exactly clockwise. So what about theta C? We found it 0.0018 rad counterclockwise. It is positive, so it is counterclockwise. Okay, so we obtained theta B and theta C. Now everything is solved for us. Everything has been solved for us. Why? Because now we can get the real value of MAB. We're going to multiply 0.1 times theta. Do you remember? This is the equation here. MAB was 2EI something. Yes, it equals to 0.1 EI theta B plus 50. So it is 0.1 times theta B. Theta B here, it is negative. Take care of the sign. Always, many of you are making mistakes in the sign convention. Okay, and then 50, which is the end here, we are going to find that it gives us something positive counterclockwise. Similarly, we are going to substitute for MBA. It is going to give us something negative, which is clockwise. MBC, it will give us some positive, so it is counterclockwise. MCB is going to be negative here, so it is going to be clockwise. MCD, it is positive, so it means that it is counterclockwise. MDC, it is positive, this means that it is counterclockwise. Okay, now we are going to apply all the moments that we have had here. We are going to apply it in our beam. So we have the moment MAB, it is counterclockwise, so it is counterclockwise here, and it is 32.9. And then on the other hand at B, it is how much? It is 71.7 clockwise, 71.7 clockwise, as you can see. Similarly for this moment here, 71.7 at BC, MBC, 71.7, it is counterclockwise, as you can see, counterclockwise, and here it is clockwise, which is MCB, it is clockwise, 49, and it's 49. Here it is, the moment is counterclockwise, 49.1 here, and here it is counterclockwise, 42.4. Sorry, 24.4, which is counterclockwise. Okay, so now this is everything on the beam. You can solve everything else. The last thing is here from the equilibrium we can obtain the reaction. This is the most important thing, the reaction here. In order to get the reaction, we need to get the shear at the points at B and at point B. B at the span AB and B from the span BC. You will get the reactions by taking the moment at any point. You have everything known for you now, the moment and the distributed load. Taking the moment at A, you can get the reaction at B. Similarly here, you can take the moment at point C, you can get the reaction at point B, and then reflect them on an opposite sign, an opposite sense on the free body diagram of B. Then the summation of the two is going to give us the reaction at B. In a similar fashion, you can apply it on the point C. Okay, so this is something that it is important to know. At the end, we are going to find that this is the reaction at B, this is the reaction at C, then this is the moment at A, this is the moment at D, and these are the external loads. Everything is known for our beam. We can draw the shearing force diagram and the bending moment diagram easily. You can check at the end that this is our equilibrium equation. Do you remember? You can check it that MBA plus MBC should equal to 0. This is right. MBA, it was minus 71.7 and MBC was 71.7, and this means 0. Similar, MCB plus MCD, they are going to be 0. This is the final check for us. After that, you can draw the bending moment and shearing force diagram. Okay, you are supposedly to be aware of how to draw bending moment and shearing force diagram. As I said, this is from the structure analysis 1. But anyway, in this course, I'm not going to ask too many times to draw it. Only what I want maybe would be some, like, what is the reaction here, or what is the moment here? This is what I am going to ask you about. Okay, so now I think that we have finished our video for today. To recap what I have said, remember well that we have gone through the main important part related to the slope deflection method, the most important equation here. You need to remember it. Remember the fixed end moments expression from where you got it. Remember the sign convention. Remember the sign convention. Yes, this is very important, the sign convention for our bending moments. And remember the application of the fixed end moments in our slope deflection equation and how to apply it after that on the equilibrium equations, and then you can obtain all the shears and the reactions of the supports. Okay, this is the end of this video. Thank you very much, and see you in the next video.